everyone. This is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, we are going to discuss about different capacities which are existing in the operation of the PN junction diode. So, while coming to the contents, in the case of PN junction diode, we may get two types of capacitances. Those are diode transition capacitance and diode diffusion capacitance. So, here we are telling that these capacitances are existing in the operation of the PN junction diode. So we will see the operation of the PN junction diode. The transition capacitance will exist in the reverse biased PN junction diode, and the diffusion capacitance will exist in the forward biased diode here. So before going to that capacitances existing in the PN junction diode, first of all we have to know the what is the actual operation performed in the case of a forward biased as well as reverse biased PN junction diode. So here, in order to construct PN junction diode, we require two pieces of P type of semiconductor material and N type of semiconductor material here. So that's why I have considered one P type of semiconductor material and one N type of semiconductor material. As we know, in the P type of semiconductor material, the holes are the majority carriers that we are indicating with plus symbol. So along with this major number of holes, we are also having some minority charge carriers. Those are electrons also present in the case of PN junction diode. And in the case of N type of semiconductor material, along with this majority carriers, those are electrons, we are also having only some small amount of minority charge carriers, so those are holes. So because of the majority carriers or more number of holes are present in the P type of material, so that's why these are called as P type of semiconductor material. Why? Because holes are having positive charge. And similarly, in the case of N type of material, why it is called as N type of semiconductor material means, in the case of N type of semiconductor material, the majority carriers are electrons and electrons are having the negative charge. So if we take these P and N type of semiconductor materials and if we join together, if we join the two pieces of P and N type of semiconductor materials, we can able to form the PN junction diode. So here, when we join the two pieces of semiconductor material, so one here the holes, the majority carriers which are present in the P type are trying to move or diffuse towards the N type of material, and similarly the electrons which are present in the N type are trying to move or diffuse towards the P type of material here. Okay, so because of this movement of charge carriers between two semiconductor materials from the junction, we may get the depletion region with many more number of immobile ions here. That is nothing but, here if I am taking one particular electron here, this particular electron, it is trying to diffuse from N region to P region, and it will combine with the holes which is present in the P region. So once this electron combining with this hole means this hole loses its original positive energy and it becomes the negative immobile ion. So this one become the negative immobile ion here. And similarly, the holes which are present in the P type of material are trying to diffuse towards the N type of material. So once this hole is moving from here to here, so it loses its energy and it is combined with the electron which is present in the N type of material. So once it is combining with the electron which is present in the N type of material, it becomes the positive immobile ion here. So because of this diffusion process of moving the charge carriers from P type to N type and N type to P type, so more number of positive immobile ions will be developed in the N region and many number of negative immobile ions will be formed in the P region. So this particular region only we are calling it as depletion region. Okay, this particular region only we are calling it as the depletion region, or also call it as barrier. Why we are calling it as the barrier here? It is once the positive and negative immobile ions are forming near the junction, means now at this particular case no electrons will diffuse towards the p side and no holes will diffuse towards the n side because of this positive and negative immobile ions present in the junction or across the junction. So that's why this region we are calling it as the depletion region. It is depleting the movement of charge carriers and it acts like a barrier to oppose the flow of electrons and holes here. So this is the case when we are not applying any voltage to the PN junction diode. So in order to make it as this particular device into conduction mode, okay, conduction mode, we need to apply the biasing for this circuit. So biasing means what here? We need to provide some external voltage to the device in order to make it into conduction mode and in order to make it operable. Okay, so here this biasing is of two types, that is forward biasing and reverse bias. So here we may apply either forward or reverse bias for the PN junction diode to see the characteristics of this one. Okay, so what is meant by forward bias and what is meant by reverse bias here? So in the case of forward bias, the positive terminal of the battery is connected to the P side and the negative terminal of the battery is connected to the N side. So if we connect the same polarity of the battery signal to the same materials, so that we can say it is in the forward bias condition. Then what about reverse bias? In the case of reverse bias, the positive voltage is applied to the N type of material and the negative voltage is applied to the P type of material here. So in this case it is the reverse bias for the PN junction diode here. So first we will see the forward bias of the PN junction diode. So if we take the forward bias, I am taking the PN junction diode with the depletion region and with the number of majority and minority carriers. So these are the negative immobile ions and these are the positive immobile ions are forming near the junction. Okay, and here we are having many holes and few electrons, and here we are having many electrons and few holes. This is P side, this is N side. Okay, and this potential we are calling it as the barrier potential VB minus plus. So for this PN junction diode, we are providing the bias positive terminal here and the negative terminal here. So we are applying the forward voltage VF. So what will happen when we apply the forward voltage to the diode here? So the holes which are present in the P type of material are trying to repel from this positive terminal of the battery here. So those are moving in this direction and those are moving towards the junction here. And similarly, the electrons which are present in this particular region are trying to repel from the negative terminal of the battery and these are also moving from this towards the junction here. So because of applying two forces, to positive force and negative force from the charge carriers towards the junction, the depletion region width will be decreases now. Okay, the depletion region width will be decreases. And if you still increase this forward voltage at some extent, the depletion region width must be 0. So there is a large movement of charge carriers in the junction. So there is a flow of forward current in the device. So always the current direction is opposite to the electron flow. So electrons are flowing in this direction. So the forward current flowing in the device is in this direction. So forward current is flowing. So once the forward current is very high in the case of a PN junction diode, so the forward resistance is very low value. In the ideal case, it is almost zero, but in the practical case, we will get it as some low value. Okay, this is the forward bias condition of the PN junction diode. And similarly, if we apply the reverse bias. So in the case of reverse bias, what we are going to do here it is, in the case of reverse bias, we are applying the negative terminal to here and the positive terminal to here. We are applying the reverse voltage. So what will happen once we apply the reverse voltage? The holes which are present in the P region are trying to move towards the battery here. Okay, and similarly the electrons which are present here also moving towards the battery. Okay, so in this way the electrons or holes are moving away from the junction in the case of a reverse bias condition. So in this case the width of the depletion region will be increases here. There is nothing but still it will extend to this particular region, and so many number of negative as well as positive immobile ions will be formed in the depletion region. So the total width is increased here. So once the depletion region width is increasing means the reverse voltage generating in the device is very, very low. Almost in the ideal case, this value may be 0 here. So though reverse current is very less, the reverse resistance is very high here. Okay, the reverse resistance is very high in the case of reverse biased PN junction diode. So now, in the case of reverse biased of the PN junction diode, we will get the transition capacitance. And in the case of forward biased diode, we will get the diffusion capacitance. So now we are going to discuss about these two capacitances and their action in the case of PN junction diode. Okay, I have already mentioned in the case of PN junction diode, we are having two types of capacitances. That is the diffusion capacitance we are representing with the CD, and transition capacitance we are representing with the CT here. So this PN junction I am taking here it as in the form of capacitor. Why I am taking here it as capacitor means the two materials, the P type of material as well as N type of material of the PN junction diode acts like a two parallel plates of the capacitor. And what is the depletion region existing between the P and N type of material acts like a dielectric medium of the capacitor here. So that we can observe here. So this is the P region we can see, and this is the N region we can see. So it is one parallel plate and this is one more parallel plate. So this P type is having all positively charged particles and this N type of material is having all negatively charged particles here. And this region is the dielectric, acts like a dielectric medium. Why? Because this one is the depletion region here. So here two materials of the PN junction diode acts like a two conductors or two plates of the capacitor, and the depletion region of the junction acts like a dielectric of the capacitor here. So these are the connecting wires here, and this indicates the electrons and these are indicates the holes or positively charged particles. So now we'll discuss with the transition capacitance. So generally this transition capacitance will exist in the reverse bias condition of the PN junction diode. So we know that in the reverse bias condition, the majority carriers which are present in the P type of material as well as N type of material are moving away from the junction here. Okay, those are moving away from the junction. So thereby so many uncovering more immobile charge carriers across the junction or in the depletion region. So because of the accumulation of more number of charge carriers in the depletion region, the thickness of the space charge layer at the junction will be increases here. So how much amount of extent it is increasing means that is depends upon how much amount of reverse voltage we are providing here. If the reverse voltage is increasing means the width of the depletion region is also increases here. So the increase in the uncovered charge with applied reverse voltage is considered as a capacitive effect in the case of reverse biased PN junction diode. So that capacitance I am calling it as a transition capacitance CT, that I am writing here as dq by dv, the variation of the charge due to the variation of the applied voltage in the device. So where dq is the increase in charge caused by change in voltage in the device. So transition capacitance we can write it as dq by dv here. And here a change in voltage dv in a time dt will result in a current here. So change in the charge with respect to time we can call it as the current. So I equal to dq by dt, given by I equal to dq by dt, and we are multiplying and divide with the dv by dt. So this one I can write it as I equal to dq by dv into dv by dt. So this dq by dv is nothing but our transition capacitance and dv by dt here. So the quantity transition capacitance CT is referred to as the transition region or space charge region or barrier or depletion region or capacitance of the diode here. So these all are the different names of the depletion region. So according to that we are calling it as the transition capacitance or reverse biased capacitance here. So this particular capacitance is not constant value, always it will vary with the applied voltage, applied reverse voltage in the device. Okay, so it is always depending upon the magnitude of the reverse voltage. Okay, so because of this reason we are writing here it as dq by dv. The transition capacitance is the change in charge due to the change in voltage. Okay, so this one we can also write it as this capacitance CT is also write it as epsilon A by W. Why we can write it as epsilon A by W is nothing but this capacitance is depending upon the depletion region width of the PN junction diode. So once the depletion region width is increasing means the transition capacitance will be decreases, and vice versa. Where here A is nothing but area of, where A is nothing but area of cross section of the junction, and epsilon is nothing but the permittivity of the semiconductor. Permittivity of the semiconductor material here, epsilon is nothing but. So we can also write it as epsilon A by W here. So if you want to derive the expression for transition capacitance CT here, we need to consider the PN junction diode with different doping levels. So one region is very high doping level and one region is having very less doping. So in this case I am going to consider the highly doped P region. Okay, lightly doped P region, or P type of semiconductor material, and heavily doped N region I am taking here. So once the P region is slightly doped means the depletion region width will be more in the P region, and once the N region is heavily doped means the depletion region width is very less in the N region. So when we are taking the PN junction diode in this particular situation, we will get it as like this. Okay, so this total region I am taking, And in this, this is the depletion region in the P region, and this is the N region. So in this case, the depletion region is high here, and here it is low here. Okay. So this is P region and N region. So width of the depletion region. So this is the width of the depletion region. We are considering only for the P region. Why? Because the depletion region in the N region is very less, but here it is very high. Because of that reason, this width only I am considering here. I am not going to consider the depletion region in the N type of material here. Okay. So this turns X equal to 0 here. And this will appear when we are providing the reverse bias to the diode. That is VR. So here unequally doped PN junction diode with a reverse biased voltage. This one. Okay. So from this we can write the equation d square V by dx square. From the junction d square V by dx square equal to Q Na by epsilon. Why I am taking only Na, why not Nd here means we are considering only the depletion region of the P region. In the P region we are having the acceptor ions. So that's why Q Na into epsilon here. So where X equal to nothing but the distance between the two junctions are measured from the junction. Okay, distance measured from the junction, how much extent the depletion region is extending because of the reverse voltage, and epsilon is the permittivity of the semiconductor material. And this epsilon we can also call it write it as epsilon naught into epsilon r here. So what is mean by epsilon naught and epsilon r here? So epsilon naught is the permittivity of the free space. Okay, permittivity of the free space. So the value of this one we can write it as 8.849 into 10 power minus 12 farads per meter. Okay, and next epsilon r is the relative permittivity of the semiconductor material. This is the relative permittivity of semiconductor material. So this value is 16 for germanium semiconductor material and 12 for silicon semiconductor material. These two values are very important while solving the problems here. So this equation I am taking it as my first equation, and next this epsilon equal to epsilon naught into epsilon r is the second equation I am taking here. Okay, so by using the Poisson's equation, we can interconnect the doping level as well as the transition capacitance by applying the integration on both sides. So for that purpose, I am taking the same equation, d square V by dt square is equal to Q Nd by epsilon. So I am integrating this equation 1 on both sides. So if we integrate it, d square V by dt square equal to integration of Q Nd by epsilon here. Okay, so sorry, here it is dx equal to dx here. So this one we will get it as dv by dx here, because integration will get cancelled with the one differentiation. So it is Q Na by Q Na here, Q Na by epsilon into x here. Okay, so here dV by dx is the electric field intensity over the 0 to W range of the PN junction diode. So from this, that electric field dV by dx, I can write it as Q Na x by epsilon. Okay, so where is the electric field intensity developed across the reverse biased PN junction diode here? Okay, and Here we can also consider the barrier potential concept while calculating the transition capacitance. So if we consider that, we will get the barrier potential VB equal to the junction potential minus the actual potential across the junction. So here this VB we can write it as the junction potential developed across the PN junction diode is QNA by epsilon minus the actual voltage is depending upon the width by 2 here. Okay, so from this we can write it as the width of the depletion region is proportional to the barrier potential under root of barrier potential whatever we are providing for the device. Okay, so now width of the width of the barrier or the barrier potential increases with the applied reverse voltage. That thing we know already. So here we are taking the net charge which is developed in the PN junction diode. I am writing here it as Q equal to acceptor NA and width of the depletion region as well as the area of the region as well as the charge developed in the region here. So here this is the total charge we are getting in the device here. So if we differentiate this dq equation with respect to V, we will get it as dq by dV is equal to epsilon A by W here. So from this dq by dV is nothing but our transition capacitance CT, that is epsilon A by W here. So from this relation we can write it as CT is always inversely proportional to the width of the depletion region here. So when we want to improve the transition capacitance, we need to maintain the depletion region width is very less here. Okay, so if we see the relation between the transition capacitance as well as the reverse voltage, I am taking the relation like this. So here I am taking the transition capacitance CT and here I am applying my reverse voltage VR here. So as the reverse voltage is increasing means the transition capacitance will be decreases here. So here suppose it is 20, some 40, 60, 80 and 100 range will be there. And similarly the reverse voltage we are taking here it as minus 5, minus 10, minus 15, minus 20 like that. So this particular reverse voltage is increasing means the capacitance will be decreases in this way. Okay, the capacitance is decreasing as reverse voltage is increasing here. Okay, so here Vj is nothing but the internally developed voltage across the junction and V is the applied reverse voltage for the junction here. So always the transition capacitance is depending upon the applied reverse voltage in the device here. So next, these things we have already derived CT equal to how much and what are the values for that CT. Yes. And next one is the diffusion capacitance. So this particular diffusion capacitance will exist in the case of forward biased PN junction diode. Okay, when we apply the forward bias to the PN junction diode, this particular capacitance will exist here. When the PN junction is forward biased, a capacitance comes into play is known as the diffusion capacitance and we are denoting this as CD here. So this diffusion capacitance value will be very high compared to the transition capacitance. Why? Because the transition capacitance is existing in the reverse bias condition but the diffusion capacitance will exist in the forward biased condition. Okay, so during the forward biased condition, the potential barrier is reduced. That is nothing but the depletion region width is reduced here. So because of that reason, the diffusion capacitance is very high compared to the transition capacitance. And the charge carriers moves across the junction and recombine here. So in this case, we are providing the forward biased or VF voltage to the P type of and N type of PN junction diode. So once we are providing in this way means the holes are repelling from here and they are moving towards the junction, and here also the electrons will repel from the battery and moving towards the junction. So because of that reason only we are getting the narrow depletion region here. So the positive and negative immobile quantity will be reduced in the case of forward biased condition. Because of that reason, the width of the depletion region also reduced here. So once the width of the depletion region is decreasing, means obviously the capacitance value will be increases here. Okay, so here what will happen, the accumulation of the holes in the N region and electrons in the P region is separated by a very thin layer of the depletion region or depletion layer here. So this depletion, the thin depletion region acts like a dielectric material or insulator of the capacitor, and the charge stored at both sides of the depletion region acts like a conducting plates of the capacitor here. So the diffusion capacitance is directly proportional to the applied voltage or electric current which is flowing in the device. So if large electric current flows through the device, a large amount of capacitance or charge accumulated near the depletion region. As a result of that, the value of diffusion capacitance will be increases here. So in the similar way, if a small electric current which is flowing through the junction, a small amount of charge is accumulated near the junction, so that small amount of diffusion capacitance will be existing in the case of diode. So always in this case also, the diffusion capacitance is depending upon the how much amount of forward voltage we are applying into the device. So it is depending upon the capacitance. The diffusion capacitance is always proportional to the forward voltage, how much we are applying for the device here. So from this discussion, I can write the diffusion capacitance is also how much charge which is developed across the junction depending upon how much voltage we are providing for the junction. So the diffusion capacitance can also be determined from the expression CD equal to tau I by eta Vt here. So here tau is nothing but the mean lifetime of the charge carrier or holes here. Mean lifetime of holes here. Okay, mean lifetime of the holes here. And next, if we want to derive the expression for this diffusion capacitance, I am considering the total current due to the electrons as well as total current due to the holes in the PN junction diode. So that is the total current at junction when x equal to 0. Okay, when x equal to 0 is given by I equal to I Pn of 0 plus I Np of 0 into A here. So here where Pn Ipn of 0 is nothing but current due to holes diffusing from P to N. Current due to holes diffusing from P region to N region, and INP is nothing but current due to holes diffusing from N region to P region. So because of the movement of holes from the two regions, we are getting the total current in the PN junction diode. So here it is, P region is heavily doped compared to the N region. In that way we are considering here. So because of that reason, we are considering only I equal to I Pn of 0 here. That is nothing but the holes movement from P region to N region. Why? Because P we are considering it as the heavily doped one. So once P is heavily doped means the more number of holes which are present in the P region only. So the diffusion current, we are writing it as Jp of x, the diffusion current. That value is minus q dp by dp dpn by dx here. So where dp is nothing but the diffusion constant. dp is nothing but the diffusion constant, and this dPn by dPn by dx is nothing but the concentration gradient. Okay, and J is the current density, how much amount of current which is flowing in the device, current density. Okay, that one we can also call it as current per area of the junction here. And IP of X is nothing but the minus QA dP by dPn by dx. Okay, or A equal to area of the cross section. Okay, and Pn of X is nothing but Pn of 0 exponential of minus xp by Lp here, where Lp is nothing but the diffusion length of the holes, how much amount of extent the holes are moving across the junction here. Diffused length of holes here. Okay, so if I'm writing dPn of x by dx is equal to, we can write it as Pn of O e power minus x by Lp into minus 1 by Lp here. So we can write it as Ip of x is equal to minus Qa dP Pn of 0 e power minus x by Lp into 1 by minus Lp here. Okay, and this one we can also write it as Ip of x equal to Qa dP by Lp Pn of 0 e power minus x by Lp here. So at x equal to 0, Ip of x value is equal to almost I here, using x equal to 0 in the above equation. So I becomes Qa dP Pn of 0 by Lp level here, Lp length here. Okay, so from this Pn of 0 I can write it as I into Lp by Qa into dP here. Okay, and from this the excess minority charge Q exists in the inside, we can write it as Q equal to integral of 0 to infinity A dP, Q, the charge developed AQ Pn of 0 exponential minus x by Lp into dx here. So after simplification, we can write the Q value as minus AQ Lp by, Lp Pn of 0 of minus 1 this values. So we can write it as AQ Lp Pn of 0 is the charge developed due to the minority carriers. Okay, so from this the diffusion capacitance, to derive this diffusion capacitance, how much we are getting here, for that purpose I am taking the Q equation again, that is AQ Lp Pn of 0, not Pn of 0, AQ Lp I divided by Qa dP here into Lp. So we can write it as Lp square into I by dP here. This both will get cancelled here. So Lp square into I by dP here. So here Lp square by dP value is tau, that is the mean lifetime of the carrier. Mean lifetime of the carrier here. And so we can write it as Q equal to now tau into L here. Okay, tau into I here. Tau into current. So from this relation we can write the diffusion capacitance CD equal to tau ID by eta Vt here. And tau is the mean lifetime of the charge carrier, and ID is the diode current, and Vt is the applied forward voltage, and eta is the generation recombination factor, that is the 1 for germanium and 2 for silicon type of diodes, and the diffusion capacitance is directly proportional to the diode current here. So in the forward biased condition, the diffusion capacitance is very, very high compared to the transition capacitance. So the transition capacitance we can neglect here. So finally I can write CD equal to tau ID by eta Vt here. Okay, the diffusion capacitance here. Okay, so in the case of PN junction diode, in the reverse bias condition, we are going to get the in the case of PN junction diode, in the reverse bias condition, we are going to get the transition capacitance, and in the forward bias condition, we are going to get the diffusion capacitance. In both the cases, the capacitance is proportional to the applied forward and reverse voltages, and always the diffusion capacitance value is very high compared to the transition capacitance. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.